Welcome to the topic of amines. Amines are organic compounds that contain nitrogen. They are important because they are used in many areas, including pharmaceuticals, dyes, and biological molecules. In this topic, we will look at their structure, properties, reactions, and how they are made. Specification, context, and learning objectives. What are amines and how are they derived? Amines are nitrogen-containing organic compounds derived from ammonia and consist of a nitrogen atom bonded to one or more alkyl or aryl groups and possessing a lone pair of electrons. Another objective is being able to explain and compare the basicity of different amines using ideas about electron density, inductive effects, and the availability of the lone pair. Amines are organic compounds that can be considered as derivatives of ammonia, NH, where one or more hydrogen atoms are replaced by hydrocarbon groups. This derivation explains many of their chemical properties, particularly their basic nature. In ammonia, the nitrogen atom has 3 bonding pairs and 1 lone pair of electrons, giving it a trigonal pyramidal shape. When hydrogen atoms are replaced by alkyl groups, such as methyl or ethyl groups, the resulting compounds are called alkylamines. If the substituent is an aromatic ring, such as a phenyl group, the compound is an arylamine. Understanding this origin from ammonia helps students rationalize trends in basicity and solubility. Amines retain the lone pair of electrons on the nitrogen atom, which allows them to accept a proton and act as Bronsted-Lowry bases. This lone pair also influences intermolecular interactions, including hydrogen bonding with water molecules, which explains why smaller amines are soluble in water. The presence of hydrocarbon groups affects electron density on the nitrogen through inductive effects, a concept that is essential for explaining differences between ammonia, aliphatic amines, and aromatic amines. Primary, secondary, tertiary, and quaternary amines, nomenclature rules for amines. Amines are classified according to the number of carbon-containing groups attached to the nitrogen atom. Primary amines have one alkyl or aryl group bonded to nitrogen and the general formula RNH. Secondary amines have 2 carbon-containing groups attached, giving the formula RNH, while tertiary amines have 3 such groups and the formula Rn. In each of these cases, the nitrogen atom still possesses a lone pair of electrons, which is responsible for their basic behavior. Quaternary ammonium salts form when a tertiary amine reacts further to produce a positively charged nitrogen center bonded to 4 carbon groups, with no lone pair remaining. These compounds are not bases in the same way as other amines because they cannot accept a proton. For primary amines, the longest carbon chain attached to the nitrogen is identified, and the suffix amine is used, such as ethanamine or propan-1-amine. The position of the amine group must be indicated where necessary. Secondary and tertiary amines are named by listing the alkyl groups attached to the nitrogen in alphabetical order, followed by the suffix amine. Alternatively, the longest chain can be named as the parent, with the other groups indicated using the prefix N-. For example, N-ethylethanamine shows that an ethyl group is attached to the nitrogen. Aromatic amines, such as phenylamine, may also be referred to by their common name aniline. Shape, bonding and the lone pair, physical properties, and solubility trends. The nitrogen atom in amines is sp³ hybridized, forming 3 sigma bonds and retaining 1 lone pair of electrons. This results in a trigonal pyramidal molecular shape, similar to ammonia, with bond angles of approximately 107 degrees. The lone pair is a region of high electron density and plays a central role in the chemical behavior of amines. It is responsible for their ability to act as bases and nucleophiles, as it can be donated to a proton or an electron-deficient carbon atom. Compared to ammonia, the presence of alkyl groups can increase electron density on the nitrogen due to their electron-donating inductive effect. The physical properties of amines, including boiling point and solubility, can be explained by their structure and intermolecular forces. Lower molecular mass amines are soluble in water because they can form hydrogen bonds with water molecules via the nitrogen-hydrogen bonds and the lone pair on nitrogen. As the carbon chain length increases, the non-polar hydrocarbon portion becomes more significant, reducing solubility. Boiling points of amines are generally higher than those of alkanes with similar molecular masses due to hydrogen bonding, but lower than those of alcohols because nitrogen-hydrogen-hydrogen bonds are weaker than oxygen-hydrogen-hydrogen bonds. Primary amines typically have higher boiling points than secondary and tertiary amines of similar size because they can form more extensive hydrogen bonding networks. Amines as Bronsted-Lowry bases, comparing basicity, aliphatic vs aromatic amines. Amines act as Bronsted-Lowry bases because the lone pair of electrons on the nitrogen atom can accept a proton. When an amine reacts with an acid or with water, it forms an alkyl-ammonium ion. For example, ethylamine reacts with water to form ethylammonium ions and hydroxide ions, resulting in an alkaline solution. Aliphatic amines are generally more basic than ammonia because alkyl groups donate electron density to the nitrogen atom via a positive inductive effect, making the lone pair more available to accept a proton. In contrast, aromatic amines such as phenylamine are less basic than ammonia. This is because the lone pair on the nitrogen is partially delocalized into the benzene ring, reducing its availability for proton acceptance. Preparation from haloalkanes and nitriles, reactions with water and acids. Amines can be prepared via several important synthetic routes. One key method is the reaction of haloalkanes with excess ethanolic ammonia, which proceeds via nucleophilic substitution to form primary amines. Using excess ammonia helps minimize the formation of secondary and tertiary amines. Another important preparation method is the reduction of nitriles using hydrogen and a nickel catalyst, or lithium aluminium hydride in dry ether. This reaction converts the nitrile group, C is identical to N, into a primary amine, increasing the carbon chain length by one carbon atom. Amines react with water to produce alkaline solutions, forming alkyl-ammonium ions and hydroxide ions. This reaction demonstrates their basic nature and is often compared directly with ammonia in exam questions. Amines also react readily with acids, such as hydrochloric acid, to form ammonium salts. For example, ethylamine reacts with hydrochloric acid to produce ethylammonium chloride. These reactions are typically fast and can be observed experimentally by the formation of white fumes or crystalline salts. Uses of amines in industry and everyday life, exam technique, common pitfalls, and key takeaways. Amines are used in the manufacture of dyes, pharmaceuticals, and polymers. For example, aromatic amines are key intermediates in the production of azo dyes, which are widely used in textiles. Many medicines, including antihistamines and local anesthetics, contain amine functional groups, highlighting their biological significance. Amines are also used in the production of nylon and other synthetic materials. In exams, remember to explain reactions using key terms such as lone pair, nucleophile, proton acceptor, and nucleophilic substitution. Always include conditions and balanced equations where required. To summarize, amines are nitrogen-containing organic compounds with a lone pair of electrons. This lone pair makes them basic and allows them to take part in many reactions. Understanding their structure and reactions is essential for A-level chemistry. Thank you for watching.